But let's see. So the starting point, first it is trying to work with Xiao Wang, who is a postdoc in Singapore, as half of the audience of this place. And the origin is very old problem, 1931, which become more famous in recent years because of the influence of the community of mass transportation. It is an extremely short summary of the problem of Schrödinger. You suppose that you have an Hamiltonian of this form and a given probability density was T0. At a later time, you observe rho T1 arbitrary. This means that you have to forget what you know about, for example, the heat equation. Arbitrary. Okay. So, the question of Schrödinger was the following. What is the most probable evolution of this density in between T0 and T1? So it is a proposition which summarizes the main element of the pool. You take V, which is continuous and bounded below. You take two density which is below zero. It's important for the uniqueness. Then there is a unique diffusion which solves Schrödinger's problem. And it solves two stochastic differential equations, which seems odd. But not so much if you remember that you are given two different boundary conditions. The first one is the usual stochastic differential equation, which is a logarithmic derivative for the drift. And another one, which is an equation for the time reverse of stochastic differential equation. Roughly speaking, this guy will remember rho T0. This one will remember rho T1. V star is a backward winner. It was known that a backward winner is also a winner. The key point, the whole point of Schrödinger, look at the equation solved by those two functions. Two-bit equation. One which makes sense with a final boundary condition, the other with an initial one. And the density, which is solution, is the product of these two guys as far as they are positive and integrable. And this represents the probability distribution of the interpolating process. Please stop there in the observation of Schrödinger. Actually, we consider only V equals 0. It was perfectly sufficient. Now, here is the point of this remark. Substitute T by minus IT. Then the density becomes an L2 product, a scalar product. There is no reason why it should be a norm, because I told you the two density are arbitrary. But a scalar product, certainly. Okay, we'll come back at the end, if there is a end, to discuss the motivation of Schrödinger, which has been a bit polemic. Let me remind you something that you all know. A classical dynamical system, that is a one form, the pointer one. Suppose that is change of variable is diffeomorphic. So you can define the action as a difference between omega 0 and an Hamiltonian dt. And this one is equal to the Lagrangian. So you have the two usual Lagrangian and Hamiltonian equation. I'm going to talk essentially about this kind of change here. A gauge transformation, a classical one. More precisely, a stochastic version of it. We all know that the action will be almost the same, except the boundary condition. When you add this term, and there is an explicit relation between the new Hamiltonian and the old one. And you can, if you like it, you can generate this transformation by a generating function called G2 in famous book of classical mechanics with a classification. Okay, what about the quantum version? The quantum version, I take the same classical object. Here is the quantization. You are supposed to accept that if you know the solution of these, you know a density because of Born interpretation. You can do a transformation of the solution of this equation, which is a very trivial one, just a multiplication by the exponential of f, and it changes very little to the original equation. The p has changed, and there is an additional time derivative of f. Now we all know that, according to Born, and maybe even more Feynman, P of its probability should be rho dq. But we all know as well that the only mathematical, probabilistic results which are mathematically consistent are Euclidean. The rest is a mystery. I'll show that to a probabilist, he will get hysterical. Where is the process? Okay. So let's do the exercise to do it in an Euclidean way. You have to change the sign of V. It's well known. This has to do with the fact that when you compute a second derivative for Newton, for example, a second derivative with respect to the time, and t comma t, you have to change this guy. Get the sign. So I copy what I did before for quantum mechanics, but I want only positive term, real term, at least. The probabilist can accept. We need a lot of positivity for probability. Okay. Stochastic geometric mechanics. A generation was learned the few pages necessary in Nikeda Watanabe, big book of the Ito school. This is something different. Actually, I don't know much about this, but the postdoc, my Chinese postdoc, who is more a geometer than probabilist, was used to this idea. Look at one form, or at a vector field. Think about the vector field. If you show to a geometer a regular vector field, no problem, he has a geometry that he can do. If you show him the infinite element generator of a diffusion, you will say, what's that? It doesn't seem to have a nice geometrical structure. The idea of Schwarz, extremely simple, as always with him, was the following. Let's call the second order differential operator the addition of what we need to do probability. Okay, for example, the second order Poincaré form is what you know, the little 2 means second order differential, and there is an addition of product of this form, which of course has been inspired by what we know about calculus. It forms a basis of this second order tangent. Okay, in the simplest possible case, you will get a second order Hamiltonian with an extra term. This is normal. The extra term takes into consideration the fact that you have an extra degree of freedom, which is the information about the diffusion of a process. So, in the simple case that I regarded, I have nice Hamiltonian equation, information involving the derivative with respect to this little o about the diffusions, and something looking like an integrability condition. Okay? PO, it's important, the additional term will be section of the second order geometric object. Section, namely P and O will be function of Q and P. Okay. Those equations are invariant under canonical change of variable, not any change of variable, a large class, and change of variable induced by the one on the M space, the base space of the Riemannian manifold. And here is the good point about the idea of Schwarz. You remember notation. This is the classical object, classical Hamiltonian. You get a new one, a deformed one, which involves an information coming from the geometry and the manifold. And naturally, the information about the diffusion. So, in the elemental case that I began, Q is simply the metric. Now, we are going to be able to copy essentially all the results of classical mechanics. When the Legendre transform is diffeomorphic, the Hamilton equations that I have written before are equivalent to stochastic Euler-Lagrange equation. Here, what should I say? There is a little delta here because we have to remember that the diffusion on a manifold has an extra term with respect to the flat case. It is the Christopher, actually. Here you have to compute a derivative, and it has been defined. It is called the damper derivative. It has been called like this by stochastic analysts. The only new thing is this guy. It is not Laplace Beltrami, as you could guess. It is Laplace Beltrami. Why? This is because we insist hysterically to follow classical mechanics. And one of the key relations in classical mechanics, you want that the gradient of the equation of Hamilton-Jacobi gives you one of the Hamilton equations. This would be exactly the case here. And the only Laplacian which is going to commute with the gradient will be Laplace. Actually, this will be the simplest one. Okay, what about the action? This will be a classical object, but computed on this regularized derivative. You can write it like this, an expression very close to the one that we had before, just here. This is geometry, and there is a special kind of integral that we need to use, which is called the Stratanovich. But the form, except for the conditional expectation, this is a classical expression. Okay, stochastic geometric gauge transform. You take your original Lagrangian, you act with a differential of f. The differential is a conditional expectation, a limit of conditional expectation. For the same reason as classically, the new one has only an addition of the two guys at the boundary of the time interval. So the new momentum are transformed like this. This one, of course, we cannot guess it. It's result from the calculation. But the good news is that the new Hamiltonian is essentially the same as classically, except for the additional term corresponding to the diffusion. I claim that there is a correspondence in Euclidean world. In my view, the idea of Schrödinger is the first Euclidean approach to quantum physics. In the simplest case, we are in 1931. probability theory as we know it does not exist. It's kind of amazing suggestion. He find a kind of analog Euclidean because he wants to find a construction which do not involve the voodoo that he hated about the interpretation of quantum theory. He just wants a problem of classical statistics. Okay, so after this quantum Gauss transformation, you get a formula similar to the one before. And here I have considered only one filtration, namely one heat equation, but the second one is good as well and allows to show the existence of the process. This one solves the regular heat equation. Now, the only good, interesting change, except the regularization, is the two drifts appear in a very special way. The sum of the two, forward and backward. This is what happened with Stochastic. As a result, for example, all the measures that you can associate with the harmonic oscillator, it's not one measure, it's an infinity of measures. Okay? All the measures associated with the Euclidean harmonic oscillator are in correspondence with the free Schrödinger, B1 0. And this formula is general and it contains, in particular, the relation between the Einstein-Rundberg and the Brownian motion, which is known since the 60s. But here you have an infinity of measures associated with the free case and with harmonic oscillator. Okay, I still have a few minutes. Good, on top. Very good. This is the part that I prefer. What was the point of Schrödinger? 1931. This was the time where he was extremely irritated by the direction of the interpretation of regular quantum theory. He started to think about, to worry about his cats. He started to find in the theory, he started to be very critical. So, this is a very natural question. Is it the problem and its solution? The solution can be elaborated in a paper that I will mention after. Is it classical statistics or quantum physics? It is absolutely classical statistics. But the genius of this idea, it is a question of statistics, which is completely original at the time. To give two probabilities arbitrarily and interpolate immediately. And the miracle is that the result is a diffusion which is perfectly time reversible. And you can guess what? The density is the integral of eta star. Morally, one solves a forward heat equation or the backward. This is essentially a time reversal. In quantum mechanics, this is, for example, Chip star, and we know in quantum mechanics this is associated with time reversal. So the problem of Schrödinger was a problem of classical statistical physics, but his real motivation was to show that there are problems of classical physics where the notion of probability appears exactly in the same way as in quantum mechanics. The same. And he succeeds. He succeeds. In the third paper, this one is very long, actually. But if you give a look to this one, you will get all the details. Second order differential geometry, this is the differential geometry of the generator of a process, in contrast with the geometry of a vector field. This one is a variation on the term statistical physics or quantum physics. And Mikami has written a little book on stochastic optimal transformation, where this is very recent, but you understood this before everybody, 10 years ago at least. And he relates this with an elementary problem of mass transportation. In some sense, what he did was to prove that Schroedinger in 1931 is somewhere between Monge, who is the father of mass transportation, and Kotorovich in the 40s. Okay, you will find more references in the paper. Thank you for your patience and yes, for your patience.
Okay, questions? Yes.
I'm afraid asking a very silly question. So you mentioned the second order differential geometry or something like second order cotangent. Does it have something to do with the jet bundle?
It has to do, actually, it seems that I confess that with the shady is that along the history, a lot of mathematicians try to construct a second order calculus.
Sure.
Okay. The difference is here, the motivation was geometrical. The answer is
Okay, thank you.
Okay, any questions or remarks? Yes.
So I don't even know if this is a question, but there was something that I didn't understand. So gauge transformations, I mean, it's clear that shifting a Lagrangian by a total time derivative doesn't change the classical mechanical systems. However, if you apply a local phase transformation to the wave function, you do change the quantum evolution, right?
yeah.
So, I mean,
But you do change because you add the term with the gradient of this function
yes.
and the time derivative inside the whole Hamiltonian.
Right. So you change the quantum evolution. So they are not exactly the same, because in one case you don't change anything, in the other case you do change quite a bit.
Yeah.
Okay. So
you are perfectly right.
okay. Thank you.
We try to follow classical mechanics, but of course we know by regular quantum theory we cannot expect to do any kind of canonical transformation. Then it would be a miracle.
Okay, any more questions? So if not, thank you again.